Welcome to the second video. In this video we're going to do the bottom side of the main PiLow board. So this is where the magic really happens on this board. There's this big chip down here which is the microcontroller, and that's actually running a bunch of code, and it's the thing which is in charge of everything which is going on down here. And next to the microcontroller there's a bunch of resistors, these resistor arrays from before. They just protect the pins of the microcontroller, and everything else is for communication out to other devices. So we've got, as well as the microcontroller, we've got this device here. This one does level shifting. The microcontroller runs at 5 volts, and the Pi, which is plugged into the other side of this board, the Pi runs at 3.3 volts. So something needs to shift the voltage levels coming out of this chip to the voltage levels that the Pi can support, and that's being done by the chip that's going to go here. And then in these two gaps, these devices with 3 legs, they're MOSFETs. They're doing a similar job to the level shifting that's done by this chip, but we're doing that off board, off this chip, so this chip can be isolated to prevent the AVR from talking to the Pi while we're programming it. So that's what's going on here. Other than that, there's some routing for power. So we're going to treat this the same as we treated the last one. We're going to pop it into the stencil, which is just below here. So I'm just going to lift that up and check that it lands in the right place. So there we go. That looks pretty perfect. No, it doesn't. Let's try again. Now it looks pretty perfect. So we're pretty good there. So just like before, we're going to take a chunk of solder paste, grab some with our spatula, put it down on the board, and then we're going to use a card to push it into place. Having had trouble using an old circuit board, I've decided to switch to this loyalty card, which is more flexible and so therefore should help push the solder in more cleanly. So here we go. So that's almost perfect. Down here we've missed a component, so let's give that another swipe. That's all good. Let's just clear the excess off the board. And then the remainder of that can go back in the pot. Obviously, if you're doing multiple boards in one row, then just keep this stacked up on the side of the stencil, and then you can use it again and again and again. Right. So lifting that up, let's have a look at the circuit board. There you go. Circuit board looks good. Let's flip it the right way up so that we can read everything more clearly. And you can see this device here, the level shifter, that has very, very closely set pins, and they have blended into each other. So just like yesterday, when we looked at the motor controller, not the motor controller, when we looked at the resistors, we're expecting those pins to clear themselves up as we go through. So I'm just going to pause now and go and get a bunch of components to put on this board. And we're back, and I've got all of the components out here now. And it's probably worth mentioning, before we go any further, what some of these numbers mean on the top of the devices. So yesterday we used a device, an array like this one, that was marked 471. This one is marked 472. Now the 471 means 4, 7 and 1 0. So the resistor that we used before was 470. This one is marked 472, which means 4700 or 4.7K. And you can see 4.7K is the value that we need here. If you look on some of the other devices, you'll see that this one is listed as 102, which is 10 and 20, 10 and 2 further more zeros. That one comes out at 1K, 100. Now, This is where it gets slightly more confusing. This one is marked 1002, and that is a 10k resistor. Now, the previous ones only had 3 digits. This one has 4 digits. Why doesn't this one say 103 to be 10k? And the answer to that is this one is a 1% resistor, so it needs more digits in order to tell you how precise it is. For our purposes, it doesn't really matter. We could use either one marked 103 or one marked 1002. It's essentially the same thing to us. So we've got our components out here, with the exception of the AVR, which is the device that goes here, and that's just not out because it's in a tray. Doesn't really fit on the screen. So as before, at this point, in fact, before this point, I want you to touch yourself onto something metal and grounded, just to make sure that you don't end up cooking anything. And then we'll go on and we'll place some of these components. Start here with a 0.1 U capacitors, and you'll see that as with yesterday, these are mounted pretty close to the circuits that they're providing power to. So you can see the power rail is this big fat one, runs down here on one side of the capacitor, and on the other side this big open slug, that is the ground. So we've got this capacitor across power and ground, and over here you'll see essentially the same thing happening, power and ground. Um, this one is cheating a little bit because it's providing a capacitor for the power rails on this device, but also it's providing a capacitor for the power rails on this device. Probably a little bit frowned upon, but we're going to get away with it. You'll note there's also another capacitor on this side. That is because this device is a level shifter. So on this side, it's got a 3.3 volt power rail, and on this side, it's got a 5 volt power rail. So it needs capacitors for both of those. Now, also, you'll notice there's the much more chunky capacitors just coming up here. These are 100 times larger at 10U. And there's one of those there's one of those for each of the 5 volt rails for the AVR. And note that these capacitors are further away, and that's just, oh, sorry, I say they're further away. Only one of them is further away, but generally you want to put the smaller capacitors as close as possible to the pins. I guess when I designed this board, I thought they were close enough anyway. So they're a bit big and a bit jumpy, so I'm going to have to be a bit more careful of them. These two diodes that go on this side of the board are Schottky diodes. A Schottky diode is used here because we want to minimize the amount of voltage drop. So all diodes have a range where they don't conduct very close to very close to 0 volts. In the case of a normal silicon diode, you'll lose as much as 0.7, sometimes as much as a volt across the diode. And if we are using a buck converter set to 5 volts, losing 1 volt across the diode would be pretty tragic. So we're using a Schottky diode which loses much less voltage, something much closer to 0.3 volts. So we've got these two diodes. The one at the bottom takes the power from this voltage regulator at 5 volts, and it directs it into the AVR. So the AVR is running off this buck converter. On the other side of the board, there's what's called a low dropout regulator, which is not a buck converter, it's a linear regulator. And those use less power when the device is drawing little power, but they use a lot more power when the device is drawing a lot of power. So when this device is running in sort of standby mode, when the pi is switched off, this device is in standby mode, we're drawing very little power, so we switch to using the linear regulator. But as soon as the power draw goes up and this device enables the power to the Pi, which is this buck converter, then it will power itself through that buck converter through these diodes. At least that's the plan. This device actually draws more power than I would have liked because of the way that the top board is designed. So maybe next time. So here, let's look at the 10Ks. Oh, no, this one is not a 10K. This one is 5100. That's 5, 1, and no zeros, which is going on the board here where it says 500. So the board is slightly mislabeled here. But this is a case where it's sometimes a little bit confusing if you don't know what you're looking at, because that might look like 5100, but of course 0 actually means 51 and nothing at all. These ones are definitely the 10Ks. So let's pop those into place. Where do they go? Down here. Oops. Where's the last 10K? There it is in the middle of the board. Now the 1K. Let's get these little transistors. These are actually MOSFET transistors, where the T in MOSFET means transistor. And they're working with this array, this set of resistors which is around them to act as a level shifter. Ooh. Actually connect to the UART on the Raspberry Pi. The UART is a type of asynchronous serial bus, and it's using the UART. It's abusing the UART and making the UART be used for reprogramming the AVR so that we can do in-field patching. But also, when you first switch on this device, the Pi should recognize that it's not able to talk over I²C and realize that the device needs programming, which is a bit of a neat feature, but it means that you have to separately power the Pi. So I'm going to drop in the level shifter now. Now, the level shifter is going to really care what its alignment is. Don't worry too much about smooshing the solder on the board. Make sure it's the right way up. Make sure the pins are in the right place. So this little circle here in the corner, in line with that little arrow there. Let's get these 1K arrays in place. I apologise for the lighting. The lighting yesterday was being done in the dark, with lights projected off the wall. Today we've moved on to using external light, so brightness will vary depending on when the sun comes in and out, which unfortunately I have absolutely no control over. Ah! Dropped that resistor in the wrong place. Let's flip that over and put it in the right place, which is over here. And then finally this 4.7K, not quite finally on the things I've already picked, this 4.7K. Now you'll notice that there's no solder has ended up on the pads which go through the board, the through hole pads. That's because those have to all be soldered by hand in a minute. So we're going to drop these into position and then heat the board up on the rework station. So that's everything with the exception of the big AVR. So let's go and get one of those from the tray. So popping the AVR down, you can see it's got a little circle cast into the corner here. That lines up with this little arrow on the board here. So the circle indicates where pin 1 is, as does the arrow. So let's see if we can get that in the right place. So I'm going to say about there. No, not quite. I've jogged it, having had it in almost perfect position. I've jogged it so it's well out of position, so that's no fun. Okay, that looks good. Everything here looks good. You'll notice these resistors are a little bit wonky, but they're touching both pads. So what we should see is once we throw that on the hot air station, those things will suddenly straighten up, which wasn't necessarily very obvious yesterday. So let's switch over to hot air station and see where we go from here. Okay, so we're loaded up on the hot air station. Things are starting to get warm. Um, we're pretty hot. It hurts to touch and hold my finger on there. Not burning myself just yet. So the settings are the same as yesterday. The IR preheat plate is set to 300 degrees and the wand is set to 370. So let's hear that. So with the heat set with the speed set all the way down, we're just going to work our way around this corner of the board until we've had a chance to warm it up. Again, like yesterday, we'll start with the solder paste being sort of dark grey. The solder paste will bake out and turn into a light grey colour, and then finally it'll go silver as it turns. You see, we're just turning silver just on these devices here, so I'm just going to concentrate on them just for a little bit. Just make sure everything properly melts. So for this board, there's less on it, which can get really upset about the hot temperatures. The board on the top, we've got both the electrolytic capacitors and we've got the LEDs, neither of which want to be overheated. This board is more able to cope with a little bit of extra heat. It's just everything on it is a little bit more difficult to solder, so that's why we started with the other board. But we're really getting through these quite quickly. We still want to wand round, even though this device here is on its own. We want to wand around because we want to make sure there's not thermal stress building up in the board. Look at that, lovely. Okay, don't forget this little 10k resistor out here on its lonesome. It often gets forgotten. We can always come back and use a soldering iron on it, but it's much better to get it done properly the first time. I'm just going to give a little bit more heat to this 1k resistor because I'm not sure it got very much heat during the original setup. Now everything is looking good again. Um, oh no, almost everything. Good. Right, so we've got at least one error on this board, which we'll have to correct in a second. If you can see it, congratulations. Um, so, like before, we're going to move this board to the side, and like before, it's become stuck because it's got bigger since I clamped it down, so I'm just going to loosen those knobs, and I'm going to slide it over here to the side, and then I'm going to work on another board, or at least you are, but I'm making these one at a time, so I'm just going to leave it here um, cooling down. Okay, I'll be back in a moment when we go to flip the board. Okay, and now for side two. A little bit of paste on the board. And our Screwfix loyalty card. Make sure it goes down in all the holes. Okay, scrape off the excess. We don't want anything left on this stencil. When you finish at the end of the day, you'll want to clear this off. Well, after you've done your set of boards that you're interested in, you'll want to go back and clean this off with IPA on a rag. Okay, so hopefully when we take our stencil off, that'll look lovely. Oops. And lovely it looks indeed. You can see this one, we're really now starting to get onto the difficult components. So down here you can see this one is just a munge of solder across all the pads. So obviously this device here is going to be a difficult one to solder. Let's see what that looks like. I'll go get all the devices. And here we are, we've got all the components that are going to go on this side of the board. So there are a couple of things going on here. The thing which is of most interest on this side of the board is this component here. This is called the high side switch. The high side switch is, sorry, I'm going to talk about this while I get on with doing these 10k resistors. The high side switch is a mix of transistors and control logic that allows us to switch and monitor some power rails. So we're using it to make sure that we're using it to switch on and off the external. That really does want to run around, doesn't it? This external socket, which is switch on and offable at 12 volts, and that can be used to run pumps, or it can be used to run external motor controllers. Also, so that's one of the two channels, and you can see comes out of these 4 pins and runs up here. The other channel, which comes out of these 4 pins and runs through this massive pad here, that runs down to the other side of the board, and it's used to power the motor controllers that are on the top face. So if anything goes wrong between the top face and the bottom face, that high side switch should see the overcurrent, see that it's a bad thing, and turn the power off. Furthermore, it should then raise a warning sign which the AVR should be able to read, and then the AVR will shuts down the system. When the AVR does that, if the AVR does that, then the AVR will start flashing the error light, which tells users that something has gone tragically wrong. Of course, that's all in software, so it does depend somewhat on the software running correctly, which hopefully it does. But the high side switch is intrinsically safe in that it will cut, well, it won't cut the power. It will limit the current to a value that shouldn't set anything on fire. It's then up to the AVR to recognize that it's limiting the current. This device really does not want to be the right way up. Just will not let go of my tweezers. Unless, of course, I want it to hold on to my tweezers. There we go, we're the right way up. Okay, let's get it onto these pads and hopefully the gooiness of the solder will hold it in place. Okay, there we go. Alright, now we're moving on to these 0.1U capacitors. Now, as before, these little devices, this one down here is right next to the high side switch. It's on the power rails of the high side switch and limiting any current, limiting any ripple that the high side switch causes on the voltage rails. And over here, the device that this is sitting next to, sorry, this is rocking around a lot more because it's now got components on the other side of the board, so it's a little bit more difficult to manage. You might choose to use a vise to hold it during this process. So this device over here is the low dropout voltage regulator, which means that it is generating these voltage lines and it needs the capacitors that are nearby to help make sure that the voltage rails don't jump about and it can do its job properly. Again, we've got a circle in the corner here of the chip, and we've got an arrow up here where it says U2, so it wants to be this way around. This one sort of almost looks comically huge when compared with some of the other chips that we're soldering, but this is actually the same size and pitch as the devices that we did on the top plate, which looked pretty small at the time. See how far we've come in just an hour or so. Oops. You see there, I deliberately turned this upside down, obviously, to show that there's a pad on the bottom of this device. That is the heat pad. This device obviously gets pretty hot, so it has to have the heat sucked out of it. You can see the heat coming in and out here. Again, dot in the corner, arrow on the board. Now, this one is really difficult to get aligned. So we're going to do our best to get it aligned on the bottom pads, because the top pads are less critical, because the top pads are shared. It's a bank of pins, bank of 4 pins for one output and a bank of 4 pins for the other output. Now finally, almost finally, I say finally because I've forgotten to get one of the devices out of the packet, which I'll have to do in a second, we get this diode. Now this is just a plain old silicon diode. There's nothing clever about this one. So this is the sort of thing that you'd find in any old rectifier. We just have to make sure that we get it the right way around. Again, here's the stripe, there's the bucket, so it points in this direction. And actually, unlike all the other ones, this one's pointing directly down to ground, and its job is to protect this device from high voltage shocks if, for instance, the power is connected back to front. I'm not sure how required it is in this particular design, but in its normal use, this is an automotive component. So it's there to protect against something called load dump. And load dump is where the alternator and the battery aren't getting on for some reason. For instance, some fool has decided to disconnect the battery while the engine's running, and the alternator at that point, like the capacitors being used in this little LDO regulator, the alternator uses the battery as a capacitor. And if you remove the battery from the system, then the alternator goes crazy and cooks all of the electronics in your car unless they are particularly protected against them, which is what this diode is doing in this circuit. So let's get this 10U capacitor in. Again, this 10U and this 1U provide the stability to the power rails over here. And then the other thing that you can get badly wrong on this board is this long connector. This one absolutely has to go in square, because as it will become apparent when you assemble this thing, the position of the Pi02W is absolutely critical. It lines up, these two pads here have got little spring pins in them, and the spring pins press against tiny little pads on the bottom of the Pi02W and pull out the USB, which runs to this connector here, which is the USB connector. So that connector constrains the Pi to make sure it's in almost exactly the right position forwards to backwards, and these pins land on the pads. They need adjusting to make sure that they specifically land on the pads. We'll do that later. But if this connector isn't in straight, then you will end up with all sorts of trouble trying to get that alignment to work properly. Okay, so we're going to go back over to the rework station now. Like before, we've got our rework station set up. So the hot plate is set at 300 degrees and the hot air gun is set up 370 degrees. Now we're going to do this pretty quickly. You wouldn't want to leave it on here for too long at that temperature, because you'll end up causing the components on the other side to drop off. So let's get the hot air gun on this, and we'll worry about the temperatures in a second. So we're waving it around to spread the heat. The connector here is the one thing that we've got to be a little bit careful of. And here we go, you see the colour is going off in the solder. This connector here will melt if we put too much heat into it, so we've got to be a bit careful about wanding the gun too close to it for too long. Okay, I'm going to start concentrating down here. There we go, that 1K resistor's just grabbed up. That diode's going to come any moment now. Again, it's on a big heatsink, so it's now over here. You see, things have not gone so well with this U5, our high side switch. You can see we made a slight error in alignment. Give it a little jog. It's kind of snapped and jumped onto the pins. That may be enough to pull it all back into place. Let's see. While we've been doing that, the other components nearby have all soldered themselves. So let's get up here to the components around the LDO. So we talked about the LDO and these capacitors which are next to it, which are just soldering up now. Oh, and look at those, all jumping up into place, that's good. these two resistors that are nearby, they're used as part of a potential divider circuit of the external on-off switch, and they're essential for the Pi to be able to read what voltage it's running at. This one here is a pull-down resistor, which is for the start button. So with all those nicely soldered, let's move our way onto this connector and see if we can get that soldered without melting it. If you look at the circuit designed for this connector, you'll see that most of it isn't really used. Down at this end of the connector, there's a lot of empty sockets. As we go further up here towards this end of the connector, we've got the UART being used for the programming. You've got these two pins at the end, which are used for power. You've also got the I2C, which is on the other side of the connector, which is used for communication. You can see as we've been wandering around on the other side, it's made this side go up much faster. Let's just get these last few pins. You can see down here, one pin, this one here, is used for the start button. That goes directly into the Raspberry Pi. Okay, so that is that soldering done. And the question is, what has gone wrong on this circuit board? Because inevitably things have. So down here on this connector, I can see already that there are pins which are shorted together. So we're going to have to come back and sort that out. We've got a couple of those on the other side as well, or at least one of those on the other side. We'll see that in a minute. So let's let it all cool down. Okay, so I've done a visual inspection of this board. I can see one error on this side, and I don't know if you can see it very clearly, but what's happened is we've got a tiny little solder bridge between these two pins. So the bottom pin here is going to ground, which is this big flood area here, and then the next pin up I think is one of the I2C pins for talking to the AVR. So what we'd find if we pushed this into production without knowing that, we'd find that we can program the AVR, we get messages saying that the AVR has been programmed, but the code will crash and not be able to run the system. So what we're going to do, we're going to come in with our soldering iron, and we're going to just touch it and see whether or not there's sufficient solder in there. We're going to touch it, and if there is little enough solder, it will just run onto those legs and we won't have to worry about things at all. But obviously before we do that, we've got to do something to make it flow. So here we go, we're adding that magic flux pen. Now I've positioned this in a way that should give you and I the best view, which means I can't see anything. I fear that what we're going to find is that on the video you also can't see anything. But what have we got? Have we managed to rescue that? I think I can still see a join there. So what I'm going to do is I'm going to add more solder. Now this might seem counterintuitive, but I'm going to add more solder here, and then I'm going to come back with the braid. So there we go. That has really soldered those together with a massive blob. Okay, so now I'm going to grab the solder braid. Here it is. I'm going to snip off the used end from yesterday. I'm going to add some flux to it. Now, putting the solder braid in place, I'm going to heat it up. And you see the solder being wicked up it's changing colour. If we lift the two away together, There we go. And now we've got two nicely soldered pins without a solder bridge between them, or apparently without a solder bridge between them. So a sensible thing to do now would be to grab a multimeter and check whether or not there's continuity there. So, probably just off camera, I'm grabbing my multimeter and there it is, it's beeping away. So if I just grab a ground pin here, there's ground to that bottom pin. Is there continuity to the second pin? There is still continuity to the second pin. So whatever I've done, I haven't solved the problem. Yeah, I can still see that problem now that I've rotated the vise into a position where I can see it with my eyes better than I can see it with the camera. So let's go back in there, give that a little longer with the solder braid. And the solder braid has disappeared. Bit out. We got solder braid here. Soldering iron. We're clamping down on the pins. I can see a wisp of flux. Has that done the job? Now back with the soldering iron. Heat up those pins. Right. And now with a reduction in solder that we did from before, those pins now look clear. So let's go back, do a continuity check again. So we've got ground, which means we should have continuity to the bottom pin, and we do. And we shouldn't have continuity to the next pin up, which we don't. So there we go. We've solved that solder bridge. Let's have a look on the other side. The other side, I think, we're going to find it's a lot more challenging. So yes, indeed, we're finding here that our little high side switch is bridged in a lot of places. We look carefully, we can see maybe it's a little bit misaligned. It's not so misaligned that I'm prepared to move it around. That's part of our problem. It was misaligned originally. So let's go in with our flux and our soldering iron and see whether just heating up the pins is enough. Starting at one end. Not feeling it at the moment. So now I'm going to add some solder. Now this is actually leaded solder. It flows slightly better than the solder which is in the solder paste, because the solder in the solder paste is lead free. Lead has been removed from solder. It's generally toxic in the environment, but it does work significantly better in electronics. So you'll find it's very common to use leaded solder in rework. It's not allowed in end user applications, so you won't find it inside your TV unless somebody has fixed your TV. And the lead-free stuff is significantly better than it used to be, but it's still not quite as good as lead. But then, that is the case with a lot of things. All the fun stuff kills you. So having removed a lot of solder off this connector, or put solder on and then removed a lot of that solder, you can see just touching it with the soldering iron has been enough to lift the pad, lift the connector. Right, so on this side we're going to find it's more difficult, and the reason that we're going to find it's more difficult is because gravity affects solder just like everything else, and as we come in from the top here, we're going to be fighting gravity to get it to come up onto the solder wick. But nonetheless, we're going to give it a go, partially because you can see slightly better if it's this way round. So we've used that bit of solder wick, so we trim it off and come back in with a fresh piece. You can see we're still wicking solder off the board. You can see it running up the solder wick. Now, as I say, on this device, these are banks of 4, so I'm not going to concern myself too much if anything is shorted between the legs of the same bank. You just don't have time for that sort of thing. So, but like the other side, this side is cleaning up nicely. So that is looking good, and now it's time to test. Now, as I say, these are banked up, so these I can't test individually whether the pins are shorted. All I can do is test whether the banks are shorted together, and they are not. So that's success as far as I'm concerned. Over here on the other side, it's more difficult to get the soldering, to get the probes in, but that's reading like continuity between 2 pins that we don't want it. How about the next one? The next one's free. Free. Oh, there's continuity where we don't want it there. And there. And there. So we've actually got a lot more continuity here than it looks like. Let's see if we can go back with the soldering iron, add a bit of heat and flux, and see if that will lift all by itself. I'm going to take the soldering iron, I'm going to give it a good swipe through the tip cleaner, which is just here, just to clean off any solder which might still be hung around on the tip here. This is quite a fat tip for this particular job. I might consider moving to a more narrow tip and seeing if that helps. Now this kind of looks like a disaster, but this disaster is one I was hoping for, because this is the hardest device to fix, and you're almost definitely going to end up in this situation. So it's good to see, walking through, that one's still showing continuity where it shouldn't. No continuity here, no continuity here. There's continuity there that shouldn't be there, none there. There's continuity there that shouldn't be there. So we're still seeing there's still quite a lot here that's showing up where it shouldn't do. I might go back with the leaded solder and just give it another go from the start with the wick. let's have another look at just those end two. Yeah, those ones are done, so that's good. So it's just down here that we have the error between these two pins, the third and fourth from the end. Let's see if we can do the same magic over there. Just actually revisiting some pins. I may regret that in a second. It turns out that I've moved the short from one place to another. That does happen. It's not the end of the world. Sometimes it can be useful to chase a short from one end to another of a device because it's easier to clear it out on the end. Okay, let's have another look. That's good. That's good. Yeah. Let's check in that the meter is still running, as this meter turns itself off, which is very useful if you're trying to save batteries, not so useful if you're checking for continuity. That was me slipping. This is looking good. So we've taken a properly messed up device. It's the thing that's got the closest pins in the entire board. We shunted across the board, most of the pins were shorted out, and now it's done and it's working. So that's good. So what's left to do on this board? Well, we believe that all the other connectors are done. All the other connections on these surface mount devices are done. So it's time to move on to soldering in the things which are not surface mount. Right, so looking at the board now with the connector, with the SMD connector on top, everything else goes in from this side of the board. All the other connectors stick upwards because the case, which is over here, obviously gets in the way of anything that sticks down. I'm going to regret that. Right, there we go. So to the connector box, let's have a look at what we've got. And so we're now on to the final stages, and here we go with the through-hole parts. So through-hole parts, like this one, sit on the board, like so, and are soldered usually from the back side. So we pop that device on the board, flip it over, and solder from this side. Now, obviously, perhaps obviously, these pins are thermally and electrically connected to the other side. So if we hold it with our fingers like this and try to solder it, we will end up with little poking spots of fire on our fingers. So be careful about that. We are going to, for the voltage regulators, which are these parts, we want to get them as close as possible to the board. In the case of this one, what I've done here is I have made the connectors so they are short at this end and long at this end. I think the ones that I made for you have longer pins on them, but the difference is that you will want to come back and trim the bottoms off. We'll see that you need to do that for a number of other things as well. Okay, so we're going to pop these devices on. Note that they are numbered, so there's a number here, number 2, which means that you need voltage regulator number 2. They are different because they're set to different voltages. So here we go. Put the soldering iron on one side of the pad and roll it towards the pins so that you've clamped the the pin and the PCB against the iron and then applying a little bit of solder, you should be able to, maybe, yep, oh dear, you should be able to get the solder to melt like so. So the general rule is apply the solder to the board and not the pad. You can see this has not gone in square. So now we've got most of the soldering done. Just put our finger on a bit of it, which isn't the bit that we're going to heat up, and then melt it, straighten it up, let it dry, and then check. Now that looks good. So we're going to now continue by soldering the rest of the pins. So the exception to the only put solder on the pad is for the first moment when you put a little bit of solder on this joint. Sometimes you don't get enough heat into the pad, so if you touch it against the iron, then it'll flow onto the pad and give you a much better thermal bond, and then the rest of the soldering can happen on the other side. There we go, like so. There's one pad down here, which is a different shape to the others. I went through and I made most of the pads so they were more easy to solder while designing this circuit board, and apparently I missed one out. Almost there. This pad is wicking away the heat, so the solder is sticking to it. It's wicking away the heat because it's a ground pad. So this soldering iron in particular hasn't got a huge amount of thermal mass, so the pad will tend to wick away the heat. We may find that's an issue later on. I may have to switch to a better soldering iron. And this one is the one that comes with the hot air station. It's not the best soldering iron in the world. I'm simply using it because it's most nearby. So now we've done these, we'll want to switch to the connectors with which are the shortest. So again, as before, we want to put the connector in and solder up one pad. I'm going to solder this one. Okay, and I'm not soldering the one at each end because this one is attached to the ground plane and this one is attached to a massive trace. You can see that's not gone on straight, which is expected. So now we've got it there and we don't need to be holding the solder. We can come back, clamp it with our finger, heat it up, and it will go loose. And then you can just let it go, like so. Let's do the easy pads. And then move on to the more difficult ones. So as I say, this soldering iron isn't the best soldering iron in the world. To get over the fact that it doesn't have a huge amount of thermal mass, I've got the temperature turned up pretty high. The temperature on this iron is set to 430 degrees, which is very high indeed. But I'm not convinced that the tip is actually running at that temperature. If you are using a proper branded one like a Heiko or Hakao, then you shouldn't worry about that. You should have that down a lot further, maybe 350 degrees or so. Right, so that connector's in. So now on to the next. The start button is over here. It's right on the end of the board. Again, we're going to take this pad. Yep, you're on camera. This pad, and we're going to solder this one because the other one is connected to the ground plane. You could do either. This one's just easier. Now that pad is done, you can look again and you see it's not straight, just like the other one. So we can come up, grab it with our fingers from behind, heat it up, reposition it so it's exactly where we want it. Okay. The black connector goes in next to it. For some reason, these are in masses and masses of tiny packaging. I can't remember if I removed them from the packaging for you or not, but they're designed, they come in a reel so that they can be mounted on a pick and place machine, which is the way that you would do this if you were a robot. But as we're not robots, I'm afraid it's all done by hand. Of course, that could be next year's challenge. Not sure how you would do it competitively. So just like before, heat it up, let it get in straight. It should fit nice and flush next to the other connector. As long as they're both in together and they sit nice and flush, then you can go back and do the other pad. There we go. This pad is taking a lot more heat out of the soldering iron, and that's because this is a ground pin. So it's connected to the board on both sides. Okay, so there we go. That's that side almost done. The last one on that side is the USB port. We're not going to do that one yet because it's super tall. So let's move on. This one is the connector that we know that we're going to have trouble with this soldering iron. We pop it into place. The reason that we know that we're going to have trouble is because it's got whopping great pins. So I'm going to solder on these lugs, and these are mounting lugs. And then I'm going to come and have a look at it with this and see whether or not we're going to have any joy at all. It will take some time. We need to put solder actually onto the iron in this case because the iron needs as much thermal connection with this pin as possible, but I'm really not seeing. Oh, no, there we go. Right, okay, so finally this pin is hot enough to take the solder. And will it also go to the board? Because remember, the board is also some massive pads. So everything is fighting against us on this one. We may have to just switch soldering iron because it's important that this is done properly. Ah, okay. It is flowing. You see how long that took? That shouldn't take you anywhere near as long if you're using a decent soldering iron. This one is really designed for surface mount rework, and by the time we get into these sort of connectors, we're well out of that range. So it worked for one, so it should definitely work for the other. It's just a matter of time before it does. Very tedious, but it's going. There we go. I think I'm going to call that as done. We can't really check the other side of the board to see whether it's made good connection, but I'm pretty sure that that's wetted down into the hole, so we're good. Right, so that connects us on nicely. That's our battery in connector. Now the next set of connectors we may find don't fit particularly well, and that's because I seem to have used a slightly different vendor when prototyping and when ordering. So these two motor controller ones go in first. So like before, except we're going to find that all of these are big staked pads onto heat sinks, so there's not a lot we can do about choosing the best one. So we choose one on each. Okay, and then come back and clamp the connector from the other side using a finger. There it goes, popping into place. Not too much force here. If you put too much force in, you'll just rip the copper pads off, and obviously that's no good for anyone. All you need is heat. Once the heat has melted the solder, it'll just slip around. There's very little that you need to do. So we've got one. Okay, and so the one that barely fits is this one. And you may find that that is just, yeah, a little bit skew in the board. And give it a good push and it will fit in. Um, it's tight, but it will do. And this one again has two connections, one of which is going to solder more easily, but both of which go big time into massive thermal pads. So this one's the ground. And I didn't do the same thing as I've done with all the rest of the connectors for that one, because the force of pushing it in and getting it in roughly square locked it into place anyway. So now probably the next thing to do is going to be this USB connector. The USB connector goes in. It has multiple chassis connections. So these are ground connections directly on to a massive ground plane. So again, this is a problem that will work better if you use a decent soldering iron. This soldering iron is a bit lightweight for the job, but it is just about managing. So while it keeps working, I'll keep using it. There we go. You can see when everything gets to temperature because it suddenly runs through, and because everything is connected to the same plane, it'll get faster and faster as you move from pad to pad. Okay, so that's the mechanical support done. Now the actual pins themselves are much smaller. So we go in from one side. Oops, let's put solder in from the other side. And go through. The ones in the middle will solder really quickly because they've got very little thermal mass. Ones on the outside, well, certainly the ground one will be a lot harder to get the heat into because it's right on a ground plane. Okay, so that's almost done. And now we get into things which are tricky. So everything here has been fitted exactly as it's meant to be fitted from the factory. These connectors, however, are not factory perfect. And the reason they're not factory perfect is because we want really a 1 by 20 connector. And it turns out the 1 by 20 connectors are few and far between, so I have had to sand the end down. In this one, I've actually sanded so far down that you can see the metal. The ones I've provided for you are sanded at one end and not at the other. So the end which is sanded goes in the middle. And we check. Oops. We check that they're right by inserting them all the way deep into the board. And they should slot all the way deep. This one I have sanded so far, you can see a gap there. Your ones, probably there is no gap. But as long as they will fit side by side like that and you're not forcing them, then you know you've got them the right way around. If you find that you are forcing them in and they are coming off at an odd angle, it's because they're in the wrong place. So just give them a bit of a shuffle. So let's leave those like that for a moment and we'll come back to those in a second. These are the next ones to worry about. These ones go into this connector, and then we want to adjust them down with our fingers, pushing them until they become flush. There, you see that? So that the black plastic is flush with the bottom of this big 20-pin connector which I've included in your box. So let's take that one and pop it down here. Let's do the next one. Works best if you have fingernails. If you don't have fingernails, you can do this with a pair of pliers if you really try carefully, or just hand it to someone who has fingernails. So because I know what's happening next, I'm putting these in further down this connector with a 1 gap in between them. Oops, I say that and then I mess it up. Right? So you see 1, 2, 3, gap, 1, 2, 3, gap, 1, 2, 3. Oops, I have pushed that one too far, so it needs to be squeezed back out again, which is tricky. Okay, but it is done. Right, so 1, 2, 3, gap, 1, 2, 3, gap, all the way along, and then that should align with these holes here. It should align perfectly. Does it? Yes. Brilliant. So now I need to get that soldered into place. Like before, because we're sat off the board, we're going to find that is a bit of a pain. So let's do the one end here. Okay. And then we're going to lift the whole thing up into place and, including this one, press that connector, this black connector, up against the board just to make sure everything is placed correctly. So we've done one end, let's do the other end, lift it, just make sure that's sat properly. There we go, click. And just this end as well. Okay, so that looks good. Now all we have to do is go back and visit all of the other pins in between. Now, it will become apparent that these pins really do stick out the bottom of the device. Electrically, of course, that doesn't matter to us, but mechanically it really does, because that's going to interfere with the case, and if it can't go in the case, then it doesn't make a proper brain, because we can't give it to any students in pieces. One of our key features of RoboCon is that it should be absolutely the lowest effort for schools to get involved as possible, and giving them something which falls apart or doesn't work properly is absolutely against the ethos of making it easy for them to get started. So it's quite important to not only get this done right, but also fully test it to make sure that what goes out of the door is the easiest thing to use. Okay, so we now have these pins in the right place to poke through the case. So the only things now left are this bank of sticky out pins here, and these two pins here. Now, I cannot show you these two pins here because they are pogo pins and they push against the bottom of the Raspberry Pi 20W, and I don't have a Raspberry Pi 20W to actually align them in the right place. So I'm going to just solder these on off camera and worry about them later. Now, for this one, we've got to make sure that this connector is at the right height. Now, what is the right height? Well, there's this shim that fits between this board and the top case. Okay, the top case plugs in like so. Now, we need to make sure that those things are the right distance apart. So what I do is I lift them up like so that they're sticking out probably about as much as they probably can. I put the shim in, and then I'm going to plug this down, but I'm not going to push it all the way. I'm going to push this down until there is a little bit of a gap. Okay, so it's connecting the connector, but it's not pushed in all the way. Now, I'm not sure we can see that easily. If I pull this connector out, it'll be more apparent. What we want to do is we want to get this in so there is about a circuit board's width. You see this pin here is very loose because this pin I oversanded. So we've got about a circuit board's width here, and that's simply because there isn't any electrical reason why the pins need to be as deep as they are, and if you make them all that way deep, it'll make it difficult to remove this out of the board. It also means that any misalignment at the next stage will be permanent. So we've got that circuit board width. We now place it through here like so, and now you can see it sticks down. You can see the level of the other circuit board, which is here. We have to get that circuit board now into place. So let's just wiggle that into place. You may have to move some pins around using the tweezers to make sure that they definitely land in place. And so there you go. Now that's in the right place, and we can go back, and with a soldering iron we can go along and solder those things. So I'm going to start at the top and work my way down. Partially because this end is the easy end to solder, because this is all the signal level stuff. The signals are all at the top here, and if you look at the circuit board, what these signals do is written on the circuit board, and that would help if you decide to stick up a scope to try and work out what's going on. So from the top, we've got VCC, which is the power. That's the 5-volt power that goes to the AVR. Then we've got NSS underscore S, which is the slave select pin for the LEDs and the logic on the top board. Then we've got SS underscore M, and that's the slave select for the motors. Then SCK, MISO, and MOSI, which are the SPI serial bus, which is what's used to talk to the LEDs and the motor controllers. And then you've got A PWM and B PWM, which are the two different motor controller speeds. Motor controller directions are controlled through the SPI connections. Then you've got some grounds, and then the power, the motor power that goes through the high side switch comes in next, and then AN, BN, BP, and AP are the signals coming back from the motor controllers. So that's pretty much it. Everything is soldered up, everything is ready to go. These pins, as you can see, far too high. So it's at this point that we come in with our handy side snips and our safety goggles. Safety goggles are essential at this point because there is going to be flying metal. These snips will fire these everywhere. You can hear it. Don't know if it's coming up on the mic, but these are bouncing around the room. I can hear 2 or 3 times before they hit the ground, and they land inside my carpet, and then when I go looking for surface mount devices, everything glitters. But you know, sooner or later I will fix the Roomba, and then it will have a go at going around my house, picking up all these little bits of metal. So that's all the metal, all the bits off this connector. Of course, we've got more connectors. We've got these ones around the back here, the 3-pin connectors, which are used for connecting to servos. So we'll take those down. And you know, just for good measure, these pins that go to the plastic connectors, the green and the blacks, they look a little bit high. So I'm going to trim those off as well. They all trim pretty easily if you've got a decent set of side snips. These ones are Nipex. They're lovely until you use them for cutting things that you shouldn't. So if you can get a set of these and store them in your soldering iron box and never use them for anything else, they are fantastic. As soon as you let someone use them to try and cut steel wire, and it's game over. So that is all of the pins taken down. You'll probably also want to take down the pins that go to the buck converters. So that's essentially done. The only thing left to do, and I will partially do it, is the pogo pins. So as long as I can find the pogo pins, I will put those in place. And of course, rather typically, I can't find them either. So not only can I not fit those in the right place, oh no, here they are. Right, okay, I have. Sorry for that minor rambling interlude. Here we go, one pogo pin, two pogo pins. The pogo pins, little spring-loaded pins. See the big rounded end up here? That's on a spring, and that means it can push against a circuit board which is pushed in from the other side. They're largely used for test situations. In fact, we are hijacking some test pins that Raspberry Pi have put onto their board in order to get this functionality. So these go into place here. One, two. And at this point now, what you'll want to do is push in a Pi 02W onto those pins and then look at the board sideways and just maneuver these, I believe, a little bit forwards, like so, until they are bang in the middle of the pads which are there. Of course, I can't do that because I don't have a Pi 02W. So I am unsure about how I'm going to hold them into place for the purposes of soldering. So let's try this. This is very janky. I apologize. I'm just going to put a little bit of solder on each of those pads. Now, if you do solder these up and it turns out that you get them in the wrong place, you can always come back with a soldering iron and just revisit those pins. You can see, in my case, they've come out pretty much facing the wrong directions, but if we're very careful, we can maneuver them into place. And obviously, you'll need a circuit board to maneuver those into exactly the right position. And there's not a lot I can do without a Raspberry Pi 20W to actually get those in the right place. So they are where they are. So we've now got a baseboard, we've got a lid, and we're done. We've finished creating that. All you have to do now is take your 3D printed parts and your Raspberry Pi 20Ws and assemble it together and turn it on. But that's for another video. So thank you very much for watching, and don't walk, do the robot.